Okay, so we'll wait just a couple seconds for people to come over from the other stream, and then I will get started. Hopefully you guys can hear me. Okay, so I'm going to go ahead and get started. I can see the chat, so if you guys have questions, feel free to please just put them in the chat, and I will probably not type the answer, but just answer them verbally. So right now, what we've got going on, one second. Hopefully you can now see the Mira user interface with the hand panel in the bottom left, and we have your sample currently loaded inside the microscope. So I've done a little bit of pre-work this time, and I started the beam. I did the beam alignments. I'll go over that quickly, but the main goal today is CL imaging, so I didn't want to spend a lot of time on beam alignment. So your sample is currently loaded. You can see here in the infrared camera that it's this time in a vertical orientation. So after Sam sent me a clarification, what I ended up doing was unmounting the plan view sample, as you can see here, and just mounting it with carbon tape in a vertical fashion. So that will hopefully let us do some CL on the cross section. Okay. So just like before, we turn the beam on. We're at 20 kV. I'm at a beam intensity of 8. The beam is running, and I'm going to start scanning. So I will tilt. You can see the cross section here. This is the sample in the middle area. I'm going to tilt so that you guys can get an idea of what the geometry is. And I do think that YouTube will record this video so you can reference it later. It should be online for a while. So this is the top side. This is the film side. I'm going to go back to 0 tilt. We're currently at a 15 millimeter working distance. That's the standard working distance for the TESCAN. That is not the working distance we'll use for imaging, though, for CL imaging. If you can see, we're looking very obliquely down the surface here. So I am going to actually over tilt a little bit until that disappears. So I'm going to take that to a -1 degree tilt. And that will just help us with setting our contrast and brightness. Okay, so just to verify beam alignment, I'm going to use this piece of debris here. We have a little bit of astigmatism in the image, but you see as I go through focus, I'm not swinging. So our objective lens is aligned, and I can select stigmator. You see that now the pad has a focus on the stigmators. Okay, so now at this point, and you can see there's still, I don't know if having the sample weight on the tabletop, I did cover it with a dust cover, but there's some stuff on the surface. We'll see if we can image through that. So we are at 15 millimeter working distance. We have a beam intensity of 8 and 20 kV. You know, by no means are these the optimum beam conditions, but we will see what the initial images look like. So what I'm going to do now is go back over to the exterior of the Gatan system. So the Gatan UI, you can see, is running here. Hopefully it's high resolution enough for you guys to see all the text on it. One thing I will tell you is I found that my YouTube player was defaulted to a lower resolution system, lower resolution setting. So you may need to go into your settings. There's a gear icon on the bottom right of the play bar. and I had to select 1020 or 1080p. So great, looks like Nancy can see it well. So I'm going to go over now to the exterior of the monocle system. Okay, so hi everyone. I'm using a second mic, so hopefully you can hear me okay. So this is the monocle system. We talked about it a little bit last training session. So the light enters here. If we're in panchromatic mode, which is where we'll start, the light is going to go straight through. Eventually, after we've set up panchromatic imaging, we're going to go to monochromatic imaging. Then a mirror is inserted and the light path comes up this way through a diffraction grating. We have entrance slits and exit slits. These are not used unless you're in monochromatic mode, but we will set these later. Again, here there's a small black knob. We have a red, green, blue filter. And so this is a red pass filter. So the red filter lets only red light through. And you can activate them by pulling until you feel a little stop. There's a spring-loaded probably ball that hits a detent, and you can feel when it's in position. This is used when people take composite images and they overlay red, green, blue to get an idea of just the different colors involved. Today we're going to operate with this all the way in, so that's all light passing through. We have the photomultiplier shutter. So to open this, and we do need to open it to operate, we're going to pull down. And it should stay down like this. So that means that now the photomultiplier is open. And then finally, and most importantly, one of the most fragile parts of the system is the mirror. So here's the mirror retraction knob. It's kind of hard to see because it's a dark knob with a black background. So now hopefully you can see it better. There's a green LED here, or an LED that is green when the mirror is fully retracted. Green means safe, that we can do regular microscopy. But now what we're going to do is insert the mirror and bring the sample up to the optimal position. Okay, so this time we've hopefully learned our lesson, and inserting the mirror, I'm going to do that with the beam off. So that will protect the beam from any gas burst that may turn the FEG module off. So now I have the CCD image up on screen. I'm going to insert the mirror, and you'll see it enter from the left side of the screen. And basically you just crank it all the way in until you feel it mechanically stop. And now we have a red LED here, and that tells us that the mirror is all the way inserted. Okay, so I see Alan's note that it's hard to hear. That's the one thing I need to figure out is the balancing of the different microphones. So the microphone I'm using now, hopefully you can hear me better with. When I'm in the external view of the monocle, I'm using the mic on top of the camera. So, okay. So here is the mirror now, and you can see that the vacuum levels are good. It's safe to turn the beam back on, so I'm going to do that. And now I'm going to drop the magnification so that you can see the mirror aperture. So before, we did not have this circular blockage. So this is a parabolic mirror with a hole in the middle. So the beam enters through the hole, and the light that's emitted is collected by that parabolic mirror. Okay. So now what we need to do is set the appropriate working distance. The parabolic mirror has a focal point that's around 6.5 millimeters. So we need to raise the sample up, and we have to, of course, be very careful while we do that. And I'm also going to do that while imaging with the CL system. So I'm going to go back over to the Gatan UI. This is digital micrograph. And actually, let's do it with the hand panels on. Okay. So hopefully now you can see here, this top hand panel is on the desktop. It's a photo multiplier controller and has a brightness and contrast knob. The very first step is we want to turn on the photo multiplier. So we just switch that to on, and then you'll see a voltage here that as I turn the knob clockwise, that voltage goes up. This is a maximum voltage of negative 1500 volts. But what you'll find is if you go all the way up, this little button or this little LED will start to flash. It says HT trip. That means you're actually getting arcs inside the photo multiplier. So I'm going to start around 1200 volts, so not all the way up. Okay. And now here in the UI, I'm going to click the button for CL imaging. And you see I already have 280,000 counts, which tells me one thing: I forgot to turn off the IR light. So we can come back here, right click, turn that off. And now obviously IR light is going to excite the photo multiplier. So we went from 280,000 counts down to 5,000 counts, which is more realistic as far away as we are from the parabolic mirror. I'm going to start a search. We're going to continue without MagCal. We have the image on the photo multiplier on the right. We have the scanning image on the left. Right now, we don't have any image information. So what we need to do is go back over to the Mira software, and we're going to click Sim External Scanning. You see now says external scanning over the image. This image is now static. But if we go back to the Gatan UI, we can now see the same region of interest. I've got a view here of both of the hand panels, so I'll use that. So you can see the monocle hand panel and the mirror hand panel. So I can operate with the mirror hand panel the same way I would if I am just in the Mira UI. I'm using the stage joystick now. I have magnification. And I have focus. I want to start the march up to 6.5 millimeters. So I don't want to go straight there because it's not very safe. So what I'm going to do, I've now got overlaid here the stage information from the Mira software. I'm going to start at 10. 10 should be nice and safe. One thing you notice, we went from an average 5,000 counts up to 6,300 counts. And I'm going to refocus. Doesn't need to be perfect. So we're at 10.073. So now let's take it up to 8 millimeters. We have 14,000 CL counts. And after refocusing, we were at 8 millimeter. So now 7 millimeter. This step is really critical. If you hit the mirror, your experiment is done and your research may be done until we repair the mirror. So it's better to creep up on it and go slowly as opposed to just going straight to 6. So you can now start to see a little bit of information. We see a dark region in the CL image because whatever this piece of junk is, it's not cathodoluminescing. But our counts are very high right now, 300,000. So what I'm going to do is we now need to find, we're close enough that we can start to find the focal point of the parabolic mirror. And I'm going to do that with this, these arrows here. So I'm going to start moving up. And you see the counts are getting much, much higher. The cathodoluminescence image is getting much brighter. And actually interesting, let me go back to the hand panel view. You can see the HT trip LED is flashing. So that tells us we need to turn this down. Photomultipliers are sensitive, and they have a lifetime. You can degrade that lifetime if you put too much signal on them. Okay, so let's tweak the focus, see about where we are. All right, so we're at about 6.7. And let's continue getting closer. Okay, and I've actually just gone through the focal point of the parabolic mirror. So that was the point I want to find and show you guys. So I've gone up through it. I need to come back down. You see this bright region? It looks like the center of the focal point is maybe off a little bit. But what I want to do is maybe even if I mag down. Okay. You see that bright spot stays regardless of the stage position. So here I'm under the focal point of the mirror. Here I'm pretty much at the focal point, and now I'm above the focal point. So we want to operate pretty much right at the focal point. And you can see again the photomultiplier was blinking, HT trip. Okay. So now what we can do is start to find a region of interest. Let me go back to the hand panel mode. Okay. So we can see we have some debris here. Whatever that debris is not cathodoluminescent. And we know that we're interested in the edge of the sample. So let's get there. So what's actually interesting here is you can see there's a difference in this interface. So your layer, whatever your layer is, to be honest, I don't know much about your material. This is much less cathodoluminescent, if cathodoluminescent at all. What we can do is slow down the scan time. You can see that the image on the left, the SEM image, is fairly sharp. The image on the right is fairly blurry. The reason why it's blurry is because we are basically the cathodoluminescence signal is a little delocalized. So it comes from a larger region, a few micron. It comes from wherever X-rays exit. It comes from where backscatters exit. So we can make a sharper image if we start to drop the beam voltage. So let's do that. So that'll require realigning the beam, because that image was just not sharp enough. Okay, so we go back to SEM, deselect external scan. It's kind of a dark image. You see we have a lot of astigmatism, so let's click Stig here. You see the hand panels have changed to Sigmator control. Drop the contrast, tweak the focus. Okay, so now let's go back to the edge of the sample, SEM, external scanning, and now back to the Gatan hardware. So you can already see it's a lot sharper image. You know, there are some interesting things happening here. I see some bright zones that are corresponding to whatever this dark region is. Of course, this is your substrate, but your coating or your growth layer here, though, does appear to not cathodoluminesce very strongly. So we're still in search mode, and we're at 16 microseconds per pixel, you can see here. What I'm going to do now is just click capture. It's going to capture 20 microseconds per pixel, and then we'll get a static image. So obviously you can see lots of hydrocarbons on the surface. What's interesting, we have this region where there's a dark signal in the CL, but I actually don't see really much of anything in the image. So what I want to do after this image acquires, just to see if I'm really having any CL signal here, because now, of course, we're off the sample, our counts are 0. I can go into here, I can digitally change the contrast and brightness, and there's something there. So there is a CL signal coming from the layer that you've grown. Okay, so we're probably going to have to make some decisions because there's such a disparity between the substrate and the growth layer. And just for experimental purposes, I'm going to try to drop down to 5 kV and see if we can sharpen up that image any. Image meaning the CL image. As we drop in voltage, the SEM image is going to get poorer resolution. 5 kV should still be good though. So every time you change beam parameters, you should tweak the stigmation. Technically, we probably should look at the beam alignment. It's close. Okay, that's probably fine for what we're doing. Back to stigmation correction. Okay, so our beam is in good shape. I'm going to come over here to a region that should be maybe free of, and I can, in this image, sort of see your interface here a little bit. So now let's go back to external scanning. And here we are again. So I'm actually going to increase the photomultiplier voltage. Actually, let me come here so you see the hand panels. Because our counts have dropped a lot. Let's see. The brightness and contrast of the CL image on the right is controlled by the hand panel. Same way that you would control brightness and contrast of the SIM image with these knobs. Okay, so maybe 5 kV is a little bit too low. Maybe the signal just drops off a cliff there. So this is part of the fun of microscopy, is just finding the appropriate settings. So we're going to go back up to 10 kV. Whoops, I hate when that happens. The high voltage was being controlled by the pad when I wanted it to be astigmatism. Okay, I'm going to find a piece of dirt to focus on. Here's one. Quick beam alignment. So I'm looking for this particle to just pulse in and out of focus and not swing. We have a minor amount of vertical swing. I went through the focal point, or through the alignment point. That's good. Okay. And now select astigmatism. Okay, so let's go back to external scanning. I'm going to go back over to the Catan UI. So something interesting that's happening, you can see this button here is pretty bright, and I have 0 counts. Let's see. Let's click off. It does say off/reset, so maybe that will reset this for us. All right. Okay, great. We're back in business. So lesson learned, if you lock out the PMT, you can just turn it off and turn it back on to reset it. Probably, when I say lock out, probably just some sort of arc or something of that nature. Okay, so I'm just looking for a region away from any obvious debris or cleavage damage to capture an image. Okay. Actually, I'm going to turn that up a little bit. And I can adjust brightness and contrast. I'm going to turn the contrast down a little bit to see if I can equalize between the layer. Yeah. Unfortunately, Gatan does an automatic histogram adjustment, so it makes correcting pretty hard. All right, let's just capture an image. Oh, I see Nancy told me I might need to switch the PMT on and off, so she's right. What we'll do after this image is move over to monochromatic mode and capture some spectrum. We'll try a spectrum from the substrate, and then we'll see if we can get one. Clearly, there's a lot of stigmation in my image, so it probably makes sense to just stop this capture, because that's not, I don't know why. It doesn't appear that there's a lot of astigmatism. Clearly there is. Personally, I find it a little hard to work in the Gatan windows, but you just have to. All right, I'm gonna hop back over to the sim window and just get a better focused image. Okay. Image parameters. External. Oops, that didn't work. Not image parameters. External scanning. Go back here. Okay, so now let's capture an image. Maybe that's not stigmation and just happens to be the features in that region are all diagonal. Unfortunately, all of that contrast that we see in the SEM image is not anything we're interested in. Okay. Where did those go? They came over here. So we can see that there are some features. All right. So now let's do this. Let's go over to do some monochromated imaging. You guys have seen panchromatic imaging. Now we'll do monochromated. And I'm going to start, because it's such a strong CL signal source, we're going to start just on your substrate. Here in the UI, I'm going to click where it says monochromatic. And if you're in the room, you will hear the diffraction grating motors turning and the mirror motors turning. So right now we're looking at 300 nanometer image. We don't see much, but what we actually want to do is, actually we're in CL imaging. We want to go to spectroscopy, sorry, still in monochromated. We're going to do a scan from 300 nanometer. Let's go to 600 nanometer. And right now we'll do a 5 nanometer, and these nanometer meaning the wavelength, 5 nanometer step size. So each bin will comprise 5 nanometers of wavelength. So this requires having a slit width of 1.85 millimeters. So what I'm going to do really quick here is go back over to the exterior. There we go. So this is where we're going to adjust the entry slit and exit slit. Whoops, and that. Okay. So we need to adjust, you can see from the UI here that the slit width needs to be 1.85. And you can also, not that one, somewhere there's a table. Nope. Well, for right now, we'll just go by what's here. So if you guys aren't familiar with reading calipers, under CL imaging. Okay, thanks, Nancy. I'll pull that up in a second. So what you see on the screen here, on the left, the calipers are set to 1.85 millimeters, which is where we want to be. And to give you an example, on the right, it's set to 2 millimeter slit width. You see that the graduations around the knob go from 0 to 50, where you see the numbers 5 and 45. So each little tick, each little division is going to be 0.01 millimeters, 10 micron. So for every full turn, you're advancing or closing these slits by 0.5 millimeter. So if we were to close them all the way, we would turn the calipers clockwise until the edge of the knob lines up with the 0. Then we go counterclockwise, and as I pass a small division on the left of that vertical rod, I'm now at 0.5. Then when I keep turning counterclockwise, I go to 1, 1.5, and then finally I settle where the 3.5 is lined up with that vertical line. So this is a standard way that vernier calipers work. You guys have probably used them, but if you haven't, let me know, and I can go over it in person here and show you how to read them. So what we want to do, though, is have our slit width set to 1.85, which it currently is because I said it before. Okay. So real quick, I'm going to take a tour here. Yeah, no. Panchromatic, under CL imaging. This one, sorry, bandpass. There we go. So this gives you an example of what your slit width will give you in bandwidth, or what a given bandwidth needs to be for slit width. So if I wanted a 10 nanometer bandwidth, I need to have a 3.70 millimeter slit width. So let's go back to spectroscopy. Okay, so we're going to start at 300 nanometer, rock the diffraction grading until 600 nanometer, and we're going to every 5 nanometer wavelength dispersion we will bend together. So let's click view, and actually you can change your dwell time here. So we've got 200 microseconds or milliseconds. I think for the purpose of expediency, I'm going to stop this. And let's see if I can just do a quicker one. And this is probably where I need some jazzy podcast music. So I do expect somewhat of a peak around 400 nanometers probably. That's where a lot of the hydrocarbons emit. Okay, so we've got a strong emitter here. On the image status, up here in the top left, as I scroll back and forth, you can see where my cursor is. So right now, this is the 365 nanometer bin, and obviously 5 nanometer wavelength difference between the bins. So you can see as I just go from one bin to the next, there's a 5 nanometer difference. So we've got a really strong emitter here, 365. So you obviously don't need to go through this full range, 300 to 600. As you plan your experiments, our full range that we can measure is 180 nanometer in the ultraviolet up to 2400 nanometer in the IR. There's a little gap around 900, I think like 850 to 900 that we just can't measure. We have to use 2 different photomultipliers. If you want to do infrared measurement, you do have to let us know, because we have to change diffraction grading, and there's a different preamp to use. We have to use liquid nitrogen to cool the photomultiplier, etc. So the bulk of CL that we've ever done in the lab is not infrared. So it's just kind of in the short UV up to the near infrared. So we're in view mode. If we were to capture one, you see that this is 5 seconds per peak, or per bandwidth. You would probably click capture and go grab a cup of coffee, come back later. what I want to do is just get a, see if we see a difference between the CL signal from your substrate and the CL signal from your layer. So I guess while we're collecting this, we'll just kind of talk through, again, panchromatic imaging. So we set the beam up and we focus and stigmate and align the beam in standard SEM imaging conditions. I set the sample to about 15 millimeter. That way I knew it would be safe to insert the mirror. At that point, I just walked over to the CL system and opened the shutter. That way we can get light to the photomultiplier, and I crank in the mirror. Once the mirror is in, then I can turn on the photomultiplier, increase the voltage, and start to raise the sample up to around 6.5 millimeter working distance. It's very important that your samples not be very large, that they be very flat, and one caveat is you should not load more than one sample at a time. If you have samples of varying heights, you can very easily damage this mirror. So we insert the mirror over in the Gatan UI. We did CL imaging in panchromatic mode. Click view, click capture, and we've captured some images. Now we've gone over to the monochromatic spectroscopy, and by clicking monochromatic mode, and then we set our starting point, our ending point, and step size, then dwell time, and we acquire. So there are some tools here. I can zoom, I can click. Does right click, converts counts to count rate, convert dispersion to EV. So here we are in EV, if you guys think more in that realm. And I believe I also can just save this text format, user data. Let's see, I'm going to make a folder for SAM. If we had clicked the capture button, this would have jumped over from our working plane into our saved plane. But we didn't do that. So I'm going to save this now. CL spectrum, serial, sure. Okay. So let's turn that off. So this is the substrate. So something around 365 nanometers. I think we already did that. Okay. So now let's go back to CL imaging. Do a quick view, and I would like to put the beam entirely into your thin film or your grown layer. Let's get that off screen. Okay. Just quickly clicking back to panchromatic just to see where we are in counts. So we have still a really good level of counts. Okay, so back to spectroscopy, monochromatic. And now one more time, view. So even though our dwell time is 0.05. The diffraction grating is on a motor and it's having to move. So I don't know, honestly, whether it moves and pauses and then dwells, or if it just discretely rocks throughout the whole range. Hang on 1 second. Okay, here we are back at 365. So what I'm hoping to see is maybe another peak. This could just be fluorescence in the substrate from X-rays, from backscatters, etc. You've got such a small layer that your interaction volume will be going into your substrate. So maybe we'll see if there's another peak elsewhere. The overall counts are much lower here than I think they were last time. Actually, maybe not that much lower, but so while we're waiting for this to acquire, one thing I will go over as well is what to do when you're done. So when we want to stop doing CL imaging, there are 3 really critical steps. One is that when you turn the PMT off here, you want to first turn the high tension all the way down. And before turning it off. That way, when the next person turns it on, it doesn't just rocket up and go really high, because that can cause some arcing. So you want to counterclockwise turn down the PMT and then turn it off. So we should see 0 volts first. Contrast and brightness does not really matter. That can be whatever. Next is you want to close the shutter for the PMT. So make sure that's closed. And then we want to remove the mirror. But the important thing is before we remove the mirror, we should lower the sample. That way, when the mirror comes out, if part of your sample is high, it doesn't drag across your sample and scratch the mirror. So in this stage, we will drop the sample and then remove the mirror. It's interesting, it does look like my camera is frozen on the hand panel, so while this collects, I'm going to see if I can reset that. All right, that's a problem to fix later. So let's go back to the Gatan UI, and it looks like we've fully acquired. So this looks pretty close to what we selected before, or what we measured before. To be honest, I don't know what we should be seeing from your samples. Okay, let's see. Oh, interesting. So it looks like maybe we had a little bit of drift. I can put the beam in spot mode too, just like you would in the TEM. So we can try to park the beam there. So I think that second time we just acquired data again, that was from the substrate. Okay, here's our same big peak we saw before. Because your layer is maybe 100 nanometers, if you were to image this in plan view, you would get definitely probably some signal from the substrate. Actually, now that I say that, you probably wouldn't, because of the layer on top that would absorb the light. If you guys have an idea of what you think the emission should be, let me know. Hopefully it's not greater than 600 and we're just not looking at it. So that you can also do peak deconvolution and data fitting. We can overlay multiple images. So this is the case where if you collect one image that with the red filter, one with the green filter, and one with the blue, we can put those all together. If we have an issue, if the issue is drifting, we can also use the Mira and not have the system in external scanning. And then, of course, our SIM image within Gatan will not really mean anything, but our spectrum will be meaningful. So then we can just do drift control by doing beam shifting or moving the stage if it looks like we're getting some drift. Looks like not much is going to happen here. Okay, so we can save this, save as, we'll just call this one layer.txt. And now go out of spot mode. And we didn't really get any drifting, which is good. So that you're aware, CL imaging setup. Let's see, we want to go to CL imaging. Here's where we can tune the diffraction grading to a specific wavelength. And then when we capture the image, we now see a kind of bright image here, brighter than it was. So we're imaging at 365 nanometer only. Because of our slit width, we're collecting 5 nanometers band pass. So that's another technique that you can do is if we did spectroscopy, found the exact emission spectrum of your layer, we could then do a monochromatic image that should capture just your layer. Back to panchromatic. So I can clearly see a signal from your layer. I would really like to be able to measure that. Okay, so what I've done now is I've gone over to the Mira, and you can see that I'm using a reduced raster window and scanning just the layer. So let's go back now and just do one more. I think what I'm going to do is I am going to increase the bandwidth. So we go to 10. I have to walk over and adjust the calipers. Let's see. Okay, so I've set the calipers to 3.7. We're going to do a 10 nanometer bandwidth. And our max that we can measure is around 850, I believe, just to see if we missed anything. So if you're in the room, what you would hear right now is the motors turning the diffraction grating to reset it. Yeah, it's interesting that we see this peak here on the left. To be honest, so the diffraction grating that's in there will dictate what our starting wavelength can be. I'm not sure if 200 is achievable with that diffraction grating, but we'll try it anyway. So one possibility too is that we could be collecting at such a coarse band pass that we need to be taking high resolution spectra. So looking at the x-axis there, it looks like maybe it won't scan above 750. That could be a limit of this diffraction grading, and the system knows that. It does know which diffraction grading is in there. We have two currently inside, 1200 lines per millimeter, 2400 lines per millimeter. We own one other that if you wanted to do outside of these ranges, we would have to install for you, but it's a very quick install. It takes like 5 minutes. It is something that's a staff level install just because you open up the light box and scratches or debris can ruin your imaging. I don't know if these are statistically significant, 470, 430, or if those are just within the realm of background noise. So traditionally, statistically significant is 3 sigma over background. And you can see there's pretty high background, around 8,000 background peaks, or background counts. Oh, thank you, Nancy. So the UV ultraviolet is the 2400 lines per millimeter, and visible is 1200 line per millimeter. The 600 line per millimeter for IR we don't have installed. But looks like we've got something happening out here at 730 nanometer. So maybe there is a peak there. Let's try a monochromatic image to see if that's our layer. So we'll go back to CL imaging. Looks like that's centered at 730. So we'll go 730. Save this, save as 10 nanometer band pass. Okay, view. Oh, and I need to turn on external imaging. Okay, so yeah, so there is some sort of significant peak there at 730. So 730. That's interesting. Okay. Looks like I may have to wait for this. Oh no, now it's going back. It was going the wrong way. Okay, so interesting. At 7:30, it actually looks like I just see more of the substrate. So that may be a second emission peak for the substrate. We can come and see if 470, see if that is a significant peak. So here's where we're reading over on the right-hand side, where we're reading what the current wavelength is. And at 470, not much of anything. So that is likely a background peak, even though it's possibly statistically significant. Okay. 350 to 390. Let's go back to spectroscopy one more time. And we're going to do a smaller band pass, 350 to 390. 1 nanometer. So I need to close that slit width to 0.37. View. Okay, I'm going to put it back in spot mode. Park it here on the thin film. And let's see what that looks like. Oh, so that's actually a good point, Alan. So Alan mentioned 730 is double 365. Could be a detector artifact. Could be double counting, just like you get double counted EDS peaks maybe. So my intention of scanning with the higher resolution step size was just that maybe there was a double peak within that 365 region, one of which was the substrate and one was the layer, but it doesn't really look like that. Okay, I don't know that we're going to get any significant data here. So what I think we'll do at this point, I'm going to stop the acquisition of that, and I will start to shut the system down. So I'm going to turn the view off, so the beam is now blanked. I'm going to come back to the mirror, and we can go back to external scanning. Oh, I actually, just for good practice, should go back into panchromatic mode. I generally always start with panchromatic CL imaging before doing spectroscopy, just to find areas that are giving signal of interest. So now we'll go back to the mirror. Let's see, looks like my hand panel camera is still not live, but that's okay. So like I mentioned before, the PMT is sensitive to infrared light. Before I turn on the CCD camera, or the IR LED for the CCD camera, I'm actually going to go over and close the shutter. Okay, shutter is now closed. I can turn down the HT. And one thing you'll see to verify you've done it correctly, that our counts go to 0. Even with the shutter closed, you get some light through it, so you may have some signal here. And you also, high tension on the photomultiplier generates noise as well, so you could see counts that are just noise. But we want to see that to be 0. So right now, high tension all the way counterclockwise, flip the switch, turn it off. And now I can turn the IR LED back on. I'm going to make the window much larger and retract. Nope, sorry. I'm going to do what I told you guys to do, which is drop the sample first. So let's go straight down. You can see we drop to a safe level so that we won't scrape the mirror when we pull the mirror out. Okay, the mirror is now retracted. You can see the signal's much brighter. Let me close this down because we're not blocking those secondary electrons from the detector any longer. And at this point, I'm going to turn the beam off. Set the stage position to our position for removing samples, -215x, y0, and z60. And I can go there. And we will now vent the chamber, and that's it. So I think this video is going to stay up archived, so if you guys need to refer back to it later, it should still be available. And I may also see if I can download it just in case. But at this point, feel free to book and attempt to do some CL on your own. Obviously, if you are not trained on the TESCAN, you'll need training on the TESCAN, so you have access to the FOM calendar. So I know, like for example, I know Alex, I trained you on the Mira. I don't know if we trained you on the Rise, but if not, then it's a very simple thing. So once you have FOM access, just book time. We will be here and can help if necessary. But now with social distancing, we want to do short bursts of help instead of sitting here, obviously, now for looks like 88 minutes we've been streaming. So if you have any questions, reach out to us, send us an email. You can get us at mc2-staff@umich or email any of us directly. Thanks for signing on, and just let us know if you have any questions.